Okay, ladies and gents, so this is the 2015 D1 paper from last year. So the way this one kicks off is with a matchings question. A matchings question should be a relatively straightforward start to you guys. It's something that's easy to revise because the questions never usually differ that much. So what we do to start off with is if we have a look at this one, explain what is necessary to use the maximum matching algorithm twice. What we have here is we've got a delivery firm with 6 vans and we've got 6 different delivery destinations. Just another thing, a bipartite graph. This is a matchings graph because you've got 2 different sets of vertices. And the reason that it's necessary to use a maximum matching algorithm twice is because if we have a look at the left-hand side here, we've got 2 unmatched vertices at the moment. And when you do the maximum matching algorithm, it only matches 1 per time. So what I'd say for that one is that we have 2 pairs of unmatched vertices. And you might want to write and the maximum matching algorithm only matches 1 pair of vertices each time. Okay, so that's your first mark. The part B. There are 3 possible alternating paths that start at either D or B. One of these is D to 2 to A to 3 to F to 6 to E to 5. Find the other 2. So when you do maximum matching questions, when you start off, you've got to start off with an unmatched vertex. And what we're going to do is we're going to have a look at the possible diagram here. When we move from left to right, and then when we move from right to left, we have a look at the existing or the initial matchings. So if we start off with B, so question B, we're going to start off with vertex B, and we can see that B can be matched to 4. And then we see that if B is matched to 4, 4 is already matched to C. So when we go on and do the maximum matching algorithm, we have to say what it's already matched to. So 4 is already matched to C. So we've gone from B to 4 back here, and C can be matched to 5, which is a breakthrough. So find the other 2 alternating paths, starting from either D or B. This is going to be the first one. But as we did that, there was no choice that we could have made at any point. If we start at B, we have to go from B to 4, from 4 to C, and then from C to 5. There's no other sort of choice that we made during that. So therefore, the other possible alternating path won't start at B, it must start at D. So let's have a look. The previous one went D to 2 to A. So what we're going to do is we're going to follow this until we've got a different choice to make. So the second path, we're going to start at D, and we've got to start off at 2. So we've got to go from D to 2. And then 2 is already matched to A. And then A can go to 3. And then 3 is already matched to F. So it's looking the same so far. And then F can only go to 6 here. 6 is matched to E. Then we can see if 6 matched to E, it's got a choice. It can either go to 1 or it can go to 5. Now last time it went to 5. So here, what we're going to do is we're going to go from E to 1 instead. So 6 is matched to E, which can now go to 1, which is different to this path here. And then when we get to 1, it's unmatched, so that is a breakthrough. So that's that one. List the improved matching generated by using the alternating path. So that's part B. So part C, they're saying that we're going to use this alternating path. So D to C to A to 3 to F to 6 to E to 5. So that's the alternating path. What we're going to do is we're going to change status. So all that means that we change the minuses into equals. So D to 2, that equal goes to minus. And we've got to list the improved matching. Don't just change the status, we've now got to list the matching. So this was our initial matching, and now what we've done is we've got D matching to 2. We've got A matching to 3, so that one's no longer there. We've got F matching to 6, so therefore F and 3 aren't matching anymore. And then E's matching to 5, so that's not matching anymore. Now it's an easy mark to miss this one, so when we list a complete matching, we can say D2, A3, F6 and E5, but that's not our improved matching, because what we haven't done is we haven't listed C4 here. So just because we didn't change anything to do with C4, it's still an initial matching, so we have to write down C4 as well. That's quite an easy mark to lose, just be careful with that. So that's our part C. So now we've got to start from the improved matching you found in C, which is what we've got here. Use the maximum matching algorithm to find a complete matching. So what I'm going to do is I'm going to use one of the other diagrams that we've got here. So we've got D already matched to 2. So D's already matched to 2, A's already matched to 3, F's already matched to 6, E's already matched to 5, C's already matched to 4. So what we've got to do is we've got to start at B, and then we've got to get to 1. So if we use our question paper here on the right of the screen, and we use our initial matching, which we've got here on the left of the screen. So that's our possibles, and this is what we're already matched to over here. So we start off with B. So we see that B can only be matched to 4, but 4 is already matched to C. That equals C, and what we're heading for 1. Okay, so C can only be matched to 5 from there, and 5's already matched to E, and then E can go to 1, which is a breakthrough. We then change the status. So it's quite a repetitive process, but one that the good thing about it is that it is repetitive. So if you do a little bit of revision, it means that you should be able to do this one quite comfortably. And then once you've done that, we have now changed. B is now attached to 4, so 4 is no longer attached to C. C is now attached to 5, so 5 isn't any longer attached to E, and now E is attached to 1. And you should list the alternating path, which we have done, and your complete matching. So the complete matching now, I'm going to write this down, complete matching A to 3, B to 4, C to 5, D to 2, E to 1, and F to 6. Don't just list the ones that we've changed, list all of the ones. And there you go, that's the first 6 marks on question 1. Okay, I realise that the video will have jumped now because I've just changed the screens whilst the video was paused, so apologies for that. The next one is to use a quicksort algorithm. So what we're going to do is we're going to write out the numbers to start off with: 18, 29, 48, 9, 42, 31, 37, 24, 27, 41. And just double check here, because sometimes they say descending, sometimes they say ascending. Now you only lose 1 mark if you do the wrong way. So if you do descending order, and you only lose 1 mark as long as you've got it correct. But we're going to be doing a quicksort algorithm. So what we do is we see how many pieces of data we've got. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we do is we pick the middle one. But because we've got 10, it means that there won't be a middle one. So we choose the one just to the right of the middle. So 1, 2, 3, 4, 5. So it's going to be this one here. So if we have a quick look, 31 is roughly in the middle anyway. So I write 31, and then to say that it's been a previous pivot, I'm going to underline it, because that's what it does in the mark scheme. And then what I do is I read from left to right. So the first number I come across is 18, which is before 31, so I'll write it here. 29 is also before 31, so I'll write that one next. And the next one is 48, so I'm going to write that one afterwards. The next one is 9, which is before 31. All we're doing is we're comparing them to our pivot point. We're not trying to get any of them else in order for this one. We just need to compare it to the pivot each time. So 9 is before 31, 42 is after, 37 is after 31, and 24 is before 31, 27 is before 31, and 41 is after 31. So that's the first thing we do. Then what we're going to do, I'm going to use different colours, is we've got 2 subsets now, and each of the subsets contains more than 1 number. So what we do is we find a pivot in both those subsets. So you find it in the middle of the first subset. The first subset is that one there, and the second subset is this one here. So we do exactly the same as we did in the first part. We find the pivot, which is either going to be in the middle or just to the right of the middle. So the 2 pivots are 9 and 37. And then we're going to write them out. So I can just see by having a look at the subset, 9 is going to be the smallest one, so I'm going to write that one there. I'm going to underline it to say that I've already used it as a pivot. I'm going to also keep 31 as underlined. I'm going to keep 37 as underlined. So if we have a look at the first subset here and compare everything to 9, so 18 comes after 9, 29 comes after 9, 24 comes after 9, and 27 comes after 9. Again, all we're doing is we're comparing them to 9. We then compare the second subset here and compare them to 37. 48 comes after 37, 42 comes after 37, and 41 comes after 37, leaving us with 2 more subsets. So the 2 pivots that you choose here, again, if you can't choose the middle one, it's the one just to the right of it. So we're going to choose 24 for that one and choose 42 for this one. So I'm going to bring 9 down, 31 down, 37 down, because they're the pivots that we've already used. So I'll put 24 there and call that as a previous pivot now. And we compare this subset to 24. So 18 goes before 24, 29 goes after 24, and 27 comes after 24. Then we've got 42. So 48 comes after 42, and 41 comes before 42. Then we've only got 1 subset now which has more than 1 number, which is this one. So we're going to choose the one to the right hand side of it. got to be right of the middle, unless there is a middle. So let's bring down the previous pivots. And 18, the subsets of 1. So bring 27 down, which is a pivot, and then 29 comes after. And then we need to say stop, sort complete, as all remaining subsets have one piece of data. Usually just stop, sort complete is enough. Alan's batting scores for the final 10 cricket matches of the same season were this here. We've got to carry out a bubble sort now. So let's do the same. Oh, sorry, if we just compare this to the mark scheme, just to make sure I haven't made any mistakes. So the first one was 31, and then they see they've underlined 31, and then they've chosen 9 and 37 as the next pivots. They've then underlined 9, 31 and 37 as the previous pivots, and they've chosen 24 and 42. And then again, they underline the previous pivots, and they choose 27, and then they've underlined the previous pivots, and they've got sort complete. They've got pivot 29 in brackets. Because it's in brackets, it means that we don't need to write that down. So there's already a subset of 1, so we don't need it as a pivot. Okay. Right, so let's have a look at the bubble sort now. So we've got 72, 53, 89, 91, 68, 67, 90, 77, 83, and 75. Now when we do the bubble sort, we compare them as we go. So first thing I'm going to compare 72 and 53, and because we're putting them into ascending order, we need to swap them around. So it's going to be 53 there, and 73 is now going to go to here. So we're now going to compare this one, which is going to be 73 and 89. Now we don't swap those, sorry, 72 and 89. So 72 remains where it is. So we're now going to compare these ones, which is 89 and 91. They don't swap, so we're going to write 81 down. We then compare 91 and 68, which do swap. So 68 is going to go there, and 91 is going to go here. So we now compare this one, which is 91, and 67. So 67 goes here, and 91 will go this point. So we compare 91 and 90. So 90 and then 91 is going to go here. Compare 91 and 77, which again will swap. So 77 is going to go here, and 91 is going to go here. Compare 91 and 83, so they swap. So 83 is there, and 91 now goes here. And then we compare 91 and 75. That's it, that is our first pass. Now sometimes they'll ask you how many swaps that you've done and how many comparisons you've done. In terms of comparisons, we compared 1, 2, 3, 4, 5, 6, 7, 8, 9 comparisons, and then you'll need to count up how many swaps that we did. So that's the end of the first part. I'm going to go over the second one a little bit quicker. Again, I'm going to explain what it is I'm doing each time. So I compare 53 and 72, they don't swap. I compare 72 and 89, they don't swap. Compare 89 and 68, they do swap, so 68 goes there. Compare 89 and 67, and they swap. Compare 89 and 90, but they don't swap, so 89 goes to here. Compare 90 and 77, they swap. 90 and 83, and they'll swap. 90 and 75, and they'll swap. Now 90 and 91 won't swap, but you don't really need to do the comparison there, because once you've done the first pass, what will happen naturally is that the biggest one will go to the right if we're going in ascending order. So that one will definitely be in the correct position. done it twice, the top two will definitely be in the correct positions. So for the rest of it, you can write 90 and 91 for all of these passes. And now what we're going to do is we're going to continue until we've got them in the correct order. So 53 and 72 don't swap. 72 and 68 do swap. 72 and 67 swap. 72 and 89 don't swap, so 72 goes there. 89 and 77 do swap. 89 and 83 will swap. 89 and 75 will swap. And now we've done it 3 times, so the top 3 will be in the correct place. So now we carry on. 53 and 68 don't swap. 68 and 67 do swap. 68 and 72 don't swap. 72 and 77 don't swap. 77 and 83 don't swap. 83 and 75 do swap. And now they're going to be in the correct order. So 83, 89, 90, and 91. Then going to do the next one. 53 and 67 don't. 67 and 68 don't. 68 and 72 don't. 72 and 77 don't. 77 and 75 do. Now if you have a quick look, we can see that they are in the correct order, but we don't leave it there. Because imagine if this is a computer system, the computer system won't automatically recognize that they're in the correct order. So what we need to do again is go through, and so 53 and 67 won't swap, 67 and 68 won't swap, 68 and 72 won't swap, 72 and 75 won't swap, 75 and 77 won't swap, 77 and 83, and obviously the rest won't swap because they're in the correct place. And then afterwards you say sort complete. As no swaps in previous pass. And finally, we've got the binary search algorithm to locate 68 in the combined list of 20 scores. You must make your method clear. So when we do this, it's really, really important when we do binary search algorithms to make sure we've got a numbered list. So we've got 20 scores here. So what we're going to do is we're going to write down a list of 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And a big shout out to Harry in my class who just walked out. Fantastic. Okay, so what we do is we label 9 as number 1, 18 as number 2, 24 as number 3, and so on and so forth. So 9, 18, 24, 27, 29, 31, 37, 41, 42, 48, 53, 67, 68, 72, 75, 77, 83, 89, 90, and 91. What we've got to do is we've got to find number 68. It's not as easy just by saying there it is. So with binary search, what we need to do is we have the first number plus the last one that's in the remaining list, add them together, divide by 2. And if it's a 0.5, we need to round up. So we say, and again, it's important that you write this method down. So 1, the first in the list plus the last in the list divided by 2, which is going to be 10.5, which goes up to the 11th piece. The 11th piece is 53. So 68 is above 53. So we reject 1 to 11, which leaves us with 12 and 20 remaining. So we do 12 plus 20 divided by 2, which is 16. So 16th piece of data is 77. And we say that 68 is before 77. So reject 16 to 20. Okay, so we've rejected 16 to 20. So we've got 12 to 15 remaining. So we do 12 plus 15 divided by 2. So it's going to so 12 plus 15 divided by 2, which is the 14th piece of data, which is 72. So we say that 68 is less than 72. So we reject 14 to 15. So we're left with 12 and 13. So 12 plus 13 divided by 2 goes to the 13th piece of data, which is 68. And then we say number found. And that's it. So the key points to this is when you do this, you need to make sure you've got a numbered list. If you don't have a numbered list, chances are you're going to lose all the marks on this question. So make sure you've got your numbered list, and then you always have to do the first in the list plus the last in the list divided by 2. Say what you get, and then say what it is that you're going to reject. And then if you just repeat that process until you get to the end, and you find your number, there's going to be 3 easy marks. It's just like a lot of this exam, it's not going to be quick workings or quick marks, but they are relatively straightforward, relatively easy, because it's easy enough to revise. Okay. Okay, again, apologies for the jump in the video. Right, the next one is a Dijkstra's algorithm to find the shortest route from A to J. So what we do is, if we have a look at this one here, this is what's got to go in all of the boxes. So you've got the vertex, which is given to you, the order of labeling, the final value, and the working value. So if we do that, the first one, because we're going to start off at A, so that's going to be 1. So the permanent value is going to be 0, because we haven't gone anywhere yet. And increasingly in the mark schemes, which I've seen over the past few years, they have a working value of 0, which I don't think they insist upon, but you don't want to give them any chance to take away marks from you. And then what you do for Dijkstra's is everything you've just permanently labelled, everything coming from that vertex, you then put in as working value. So you've got, coming off A, you've got this 5, so that makes a 5 there, and you've got 12 down there. So then what you have to do, once you've done everything that's coming off from that one, you have a look at the smallest working value. So the smallest working value is 5. So this is now the second one we've labelled, and we make it permanent. Now, once you make something permanent, every arc coming off there, you need to add on to it. So 5 plus this 6 gives us 11. 5 plus a 2 gives us 7. And then once you've updated all of the vertices that are coming off the vertex that you've just made permanent, you then see which has got the smallest working value. So we've got 7 and we've got 11, so 7 is the smallest. So therefore we're going to make this one F as the third one and make that one permanent. Now coming off F, we've got D over here, so that's another 2, so that's going to be 9. And then G, 7 plus the 8 is going to be 15. So now we've got 9, we've got 15, and we've got 11. So the smallest there is going to be D. So we're going to make that the fourth one. We make that permanent as 9. And then we do everything coming off D. So G is coming off D, so if we add 9, so if we add this 5 on to 9, that's going to make 14. E, if we add 10 on, that's going to be 19. And we've got C coming off it, so if we add 1 onto that, that's going to be 10. That's everything coming off D. So now we have a look at all of these. So we've got 14, we've got 10, we've got 19. So the smallest from that is going to be 10. So we make that one our next one. So that's going to be our fifth one. And we make that permanent, which is 10. So everything coming off C, that's not already permanent. It's just E. Because, I mean, we've got this arc, and this arc, but all of these lead to permanent vertices, so we don't need to worry about that. So the only new one coming off, which isn't permanent, is E. So we need to add on this 7 to make 17. So we've got 14 and we've got 17. So we make this one permanent, so that's going to be 14, and that's going to be the sixth one which we've made. So everything coming off this one, that's going to be 16, this is going to be 15 because we add 1 onto the 14, and we add the 9 onto the 14, which makes this one 23. So now we've got 15, 16, and 23. So the next shortest, excuse me, is a 15, so that's going to be 7, or the seventh one, which is 15. So if we have a look, this one is 5, but that's already bigger than 16. So what they'll have in the mark scheme, they'll probably have a 20 in brackets, but we don't need to put that 20 in because 15 plus a 5 isn't smaller than our current working value. But 15 add the 7 makes 22. So then we've got 16 as the next smallest, so that's going to be 8th one. We make that one permanent. And then there's nothing new coming off E. So the only one remaining is going to be this one, which is 9, which makes 22. So if we just double check that against the mark scheme. So we've got 1, 0, 0, 2, 5, 5, 3, 7, 7, 4, 9, 9, 5, 10, 12, 11, 10, 6, 14, 15, 14, 9, 22, 23, 22, 7, 15, 15, 8, 16, 19, 17, 16, with that 20 in brackets, like I said. But you don't need to have that one. So the question then says, state the shortest route and its length. So to get from A to J, the length of it is 22, because it's the permanent label. And the shortest, we've got to see how we get the shortest route. And if I do part A and part B at the same time, it says explain how you determine the shortest route from your label diagram. So we ended up at J. So something plus the 7 makes 22. Now 14 plus 7, sorry, 14 plus 9 doesn't equal 22, but 15 plus 7 does equal 22. So therefore H was the one preceding it. So the way I'd explain it, and this is the easiest way to do, the last one was J, so J take, so 22 take away 7 equals 15. So therefore, we've gone from H to J. So that's one of the lengths. Then 15 take away, so 15 take away 5 doesn't equal 16, but 15 take away 1 does equal 14. So I'd say that 15 take away 1 equals 14. So therefore, GH is going to be a length. Okay, so now we're here. So 14 take away 2 doesn't equal 16, 14 take away 5 doesn't equal 9, but 14 take away, sorry, yeah, let's try that again. 14 take away 8 doesn't equal 7, but 14 take away 5 does equal 9. So I would say that 14 take away 5 equals 9. So therefore, that's going to be D to G. So D is the next one previous. 9 take away 1 doesn't equal 10. 9 take away 10 doesn't equal 16. But 9 take away 2 does equal 7. So I'll say that 9 take away 2 equals 7. So FD is going to be the next one. And 7 take away 2 equals 5. So I'll say that 7 take away 2 equals 5. So that's going to be BF. I'll make sure I've written that down. And then 5 take away 5 is 0. So AB is in there as well. So the shortest route is A, B, F, D, G, H, J. And the way we figure that out is we do the permanent, what do they call it, the permanent value, take away the arc length, that should equal the previous permanent value. You have to do that all the way through. Now what you can do is you could try and explain that in words, but you've got to be really, really thorough with your explanation. Or if you just say that this permanent value take away this arc equals this permanent value, therefore it's going to be HJ, and then do that all the way back to the beginning, that's enough to get you the marks. The next one says find the shortest route from A to J via E and state its length. Okay, so let's get rid of a bunch of the stuff that we don't need here. Okay, so if we have a look at, so we've got to go to E. Now the good thing about this is that all the permanent values here, what they do is they tell you the quickest way, or the shortest amount of time to get to this vertex. So the shortest amount of time to get to E is going to be 16. So let's have a look at how we do that. So 16 take away 2 is 14, 14 take away 5 is 9, as we know, there. So the shortest way to get to E, so this is part C we're doing here on this question. So the shortest way to get to E is A to B to F to D and then to E. And then we've got to get to J. So we've got to find the shortest way to get from E to J. Doesn't matter if we go back along any paths. So we could go 5 and 7, that's another 12. Or we could go back to G and then back to there, which would be 11. Or we could go back to there, and then back to there. And if we do that, so we've just got to have a look at different ways to get from E to J. And if you spend enough time looking at it, E to G is going to be 2, G to H is going to be another 1, and then H to J is going to make it down to there. So to E, that's 16 so far, and then back to G, oh sorry, my mistake. When I was saying how to get from A to E, it's A, B, F, D, and then G, and then E. My apologies if you spotted that. Okay, so then when we're at E, we then go back to G, and we go to H, and we go to J. And the length of that, to get to E, we know that it is 16. Then we've added on another 2 to get back to G, another 1 to get to H, and then we've got another 7 to get to J. So 16 plus 2 plus 1 is going to be 19, plus another 7 is going to equal 26. Okay, so the next part of the question, let's move it over there, is this one here. So again, it looks like another graphy question, and then what you've got to do is you've got to look out for the key parts to what the question is asking you for. If you have a look at this, um, we've got the first thing here, which we'll come to in a second. But then if you have a look through the question, um, it tells you about a minimum length where you traverse each road. So as soon as it starts talking to you about that, you are looking at route inspection. But we'll get to that in a second. The first one, explain why a network cannot have an odd number of vertices of odd valency. The reason being is if you have an arc, each arc will go to 2 different vertices, and then each extra arc that you put in will add another 2 to the total number, because it'll add 1 more to this vertex and 1 more to the other vertex it goes into. So then you add another one, that's going to be another one that you add to it. So what you need to say is that each arc will add 2 more to the total valency. Now valency is where you add all the degree, or all the, so the valency, for instance, of this one would be 3, because you've got 3 arcs going into it. So each one arc adds 2 more. It'll add 1 to that one, it'll add 1 to this one here. So each arc will add 2 more to the total valency of the graph. So the total valency equals 2 times the number of arcs. So if you have the number of arcs and then if you double it, that's going to be the total valency. So therefore, this will be an even number. Now, if you have an odd number of vertices with odd valency, you're going to have an odd number of odd numbers will equal an odd total. Because an odd times an odd lot of an odd is an odd total. So therefore, we can't have an odd total because the total valency will always be even. Okay, now that we've got that cleared up, let's have a look at part B. So figure 4 represents a network of 13 roads in a village. A number on each arc is the length in meters of the corresponding road. A route of minimum length that traverses each road at least once needs to be found. The route may start at any vertex and finish at any vertex. Write down the vertices at which the route will start and finish. So what we need to do, excuse me, is we need to have a look at the valency of all of these. So here, that one there is going to be an even. That's 2. This one here is 3. That's got 3 arcs going into it. 1, 2, 3, 4 for that one. This one's got 2 going into it. 1, 2, 3, 4. That one's got 2 going into it. This one 1, 2, 3, 4, 5, 6. So we've got 2. So we've got 2, 1 there and 1 there. Not sure with the middle arrow there. We've got 2 vertices there that have got an odd valency. So an odd number of arcs going into it. So if you go back to when you started learning about this, if you are going to draw a diagram without taking your pen off the table, so off the paper, you've got to start at one odd vertex and end at the other odd vertex. Now here we've got 2 odd vertices. We've got D and we've got E. So therefore we've got to start at D and then end at E. And this is called semi-Eulerian, which means that you can draw the shape without taking your pen off the paper, but it means that you've got to start at one of the odd ones and end at the other one. Now what this question is usually all about is being able to draw it where you start and finish at the same vertex. And if you're going to do that, you need to make it fully Eulerian, or just Eulerian, or another word for it is traversable. So in order to do that, you need to have all of them as even. Now, if they're not all even, if you've only got 2 that are odd, it means that you can start at one and end at the other. If you've got more than 2 that are odd, it means that you've got to start linking them together. So for part B here, we've got to start at D and end at E, or the other way around. Okay, next, a new road AB of length 130 meters is built. So A to B, and that's going to be 130 meters. A route of minimum length that traverses each road, including AB, needs to be found. The route must start and finish at A. So we're going to start and finish at this vertex here. Use the route inspection algorithm to find the roads that you will need to traverse twice. So what we do, as soon as it says route inspection algorithm, what you need to do is you need to find all of the arcs, so all of the vertices which are odd. So this one here is odd, this one here is odd, this one here, B, is now odd, that's got 3, and A is now odd. So route inspection algorithm, what you've got to do is you've then got to do a combination of A, B, D, and E for all the different combinations. So I can do A, B, and D, E. What other combination can I have where I've got 2 pairs? I can do A and D, and B and E, or I can do A and E, and B and D. So now what we have to do is we need to try and find the quickest or the shortest way of connecting all these. So I need to find the shortest way of connecting A to B. And usually there isn't directly A to B. So if you have a look here, A to B is 130, or if I go from A to C and then C to B, that's actually going to be 120. I'll write down 120. Now what's the shortest way to get from D to E? So I could either do 320, or I could do 250 plus 80, which is going to be 330, or I could do 90 plus 100 plus 150. The shortest way to do it, I think, there is going to be doing, oh no, tell a lie. I can do from D to B, from B to C, and then from C to E. So that's going to be 170 plus 50 plus 80, so that's going to be 200. No, it's alright, it's going to be 300. Let's try that again. Okay, like I say, they usually don't have a straightforward D to E. So if I add up the total, that's going to be 420. And even though exams aren't designed to trick you, this one it sort of is. It tries to trick you to find, or try and catch you out so that you're not being that observant. Next one, we've got to find the shortest way to get from A to D. So we can go A to B, which we know is going to be 70 plus 50, which is 120, plus 170. I think that's going to be the shortest way. So that's going to be 120, it's going to be 290. And then B to E, the shortest way is just going to be 50 then 80. So that's going to be 130, which gives us a total of 420. So I'm hoping that the other one is going to give us a shorter route, because these two are the same. So I'll try and find A to E. Now A to E, if you look, it's going to be just 70 then 80. So A to E is going to be 150. B to D is simply 170. If we add those together, it's going to be 320. So if we go back to this question, and hopefully after a while that will be a lot quicker for you to do. Like I say, we're taking our time on this video, so as soon as you go through more of these questions, it should be a lot easier. Use this route inspection algorithm to find the rows that will need to be traversed twice. So we're going to be using this one. So to get from A to E, we traversed this road and then this road, which made 150, and then B to D was just this road here. So for part C, we need to traverse B, D, AC, and CE need to be traversed twice. And the length of the entire network is 2090, plus we need to add on these extra routes, or these extra lengths here. So it's going to be 2090 plus 320, which is going to be 2410. Oh, my apologies. You don't need to do that for part C. It says calculate the length of a possible shortest inspection route. So that's what it is. So this part here is going to be part D. It's going to be the existing weight plus the additional weight which you've added. So that's going to be the 2410. Okay, and then what they'll do is they often chuck in that this is the third part to the question. It's now time to start and finish inspection point at two distinct vertices. So as soon as it says that you can start and finish at different points, it means it's only got to be semi-Eulerian. And as we said earlier, well, that means that we can have two of them which are odd. So calculate how much shorter the length of this route is compared to the length of the route in D. You must make your method and calculations clear. So if we have a look at our workings for part C, which we need to make sure that we make clear in part C, the shortest route between any of these is A to B, which is simply 120. So if we keep that one as the route that we need to redo, what we can do is that we can start at D and we can end at E. So we can start at D, end at E, which means that the only ones that we need to traverse twice are to get from A to B, which is going to be this one and this one. So calculate how much shorter the length of this route is compared to the length of the route in D. So the length of the route in D was 2,410. What you then need to take away is this 2,090 plus 130 plus the extra routes, which are going to be 70 plus 50, because they're the ones that you need to traverse twice. Or you can add up the route that you need to do traverse twice and just work out the difference. Either way is absolutely fine. This here actually works out the difference. So 2090 plus 130 plus 70 plus 50. So it's going to be 2,410 take away 2,340, which makes a difference of 70. So we've started at D and ended at E, so we don't need to traverse D to E. The only thing we need to do is traverse A to B. So by doing A to B, we've made it semi-Eulerian. So therefore, we're going to save ourselves 70, whatever the units are, 70 meters, 70 miles, or meters. And that's it, that's all we have to do for that one. Okay, so let's have a look at the next question. We're going to use Kruskal's algorithm now. So minimum span and tree, what we've got to remember for Kruskal's algorithm, so basically what we're doing is we're going to find a way to link all of the paths together so that we don't make any loops. The whole thing with spanning trees or minimum span trees, we can't have any loops. And the way we do it with Kruskal's is that we start from the shortest one and we keep going until we get to the biggest one. And we reject them if they're going to make an arc, or sorry, make a loop. So as such, what we do is we start with the shortest one, which is BC. So I'd say BC. And then the next shortest after 6 is 7. Now this is where it's easy to make a mistake. So what I would do is I would actually either do a separate diagram or draw over these things to show what you've already done. So A, B is the next one I'm going to do. And then the next shortest after 7 is 9. Now, even though we're not going to choose it because it would make a loop, so we don't choose it, but we need to say that we've had a look at it. So AC, and then we reject. Then the next one after 9 is, there's a 10 there. So DE. Next one after 10 is 11. So DC. Next one after 11 is no. Sorry, let's get rid of that because in fact, if we do this in a slightly different colour to show which ones we've rejected. The next one after 11 is 12, 13, which is DF. Next one after 13 is 14. So if we chose CE down here, that would make a loop. So we're going to say CE, but we reject it. The other 14 is this one up here, but again, that would make a loop. So we reject that one. But we need to say that we've considered BF, and then we've rejected it. So after 14, got any 15s? Yep, down here, so EJ. 16 we've got up here. So it's going to be FH. Next is going to be 17, but if we do 17, it's going to give us a big loop again. So HJ. HJ, and we reject that one. After after 17, there's no 18, so we've got 19, but that's going to make us a loop. So BD, we reject it. So what we just rejected, 19. So 20 is the next one, which is GH, and that's it. And that is our minimum spanning tree. And what you could then do is you could list the rest of them and say that you reject them, but you don't need to do that. They're only looking at this. Or you might want to say reject the rest, because they'll all make loops. Okay, so starting at G, we've now got to use Prim's algorithm. In fact, if we just show the mark scheme for this one, so um, 4, we've got 5 now. So we've got BC, we've got AB, we've got AC, which we rejected, or not AC as they've put, DE, CD, DF, not CE or not BF, and it doesn't matter which way around we write that. Next one was EJ, FH, not HJ, not BD, and then GH. They haven't listed any others. So now what we've got to do is we've got to do Prim's algorithm. Okay, so Prim's, what we do is we start at G, and then we've got to do the shortest one, which is attached to our existing tree. So starting at G, the shortest one that we're going to do is H. So GH is going to be the first one we do. And then the shortest one attached to either G or H is this one. So that's going to be FH. Next one we're going to do, the shortest one that's attached to either G, H or F is 13. So we're then going to do DF. Next one after that is going to be 14. No, it's not, sorry. I always make mistakes on these, so apologies. The next one is going to be DE, which is 10. The shortest one attached to any of them so far is going to be D to C. You can write it as either DC or CD, doesn't matter. The shortest one then attached to what we've got is this one here, which is CB or BC. Shortest one attached now is AB. The shortest one that doesn't make a loop is going to be EJ. And that's it. That's all you need to do for that one. If you have a look, it's GF, FH, DF, DE, CD or DC, BC, AB and EJ. And the next question they ask is, which is going to be 98 kilometers, is to find the weight of the minimum spanning tree. So we're going to add up all our numbers here. So we add up 7, 6, 11, 10, 15, 20, 16 and 23. If we just double check that, so on the calculator, plus 6 plus 11 plus 13 plus 10 plus 16 plus 20 plus 15 equals 98. So I'd write down 7 plus 6 plus 11 plus 13 plus 10 plus 16 plus 20 plus 15 equals 98 kilometers. Okay, now the next one is a little bit trickier. So if we get rid of this, we've got a connected graph which has n nodes. So what I'll do is, as soon as it starts talking about this, I'll do a little diagram just to see what it is that we're talking about. So let's say we've got 3 nodes. It's a connected graph, so we've got that. So sorry, just quickly, a connected graph everything doesn't need to be connected to everything else. So anywhere we can get from any so any vertex to any other vertex is what we call a connected graph. So a connected graph is n nodes. The sum of the degrees is m. The graph T is a minimum spanning tree of V, in which case let's have a couple more in here as well. So the sum of the degrees is m. And so we've got V here. And the sum of, if we add up 1 plus 2 plus 3 plus 2 plus 2, that equals m. So we can say here that m equals 1, 3, 6, 7, 8, 9, 10. And we've got to write down the number of arcs in V. So 1, 2, 3, 4, 5. So the number of arcs equals 5. Now why is that? Why is the sum of the valency double the number of arcs? As we said earlier, each arc will add 2 to the valency because it connects to 2 vertices each time. So if we have m, which is the sum of the degrees, if we divide that by 2, that is going to be the number of arcs. So write down in terms of m the number of arcs in V, it's going to be m divided by 2, because it's going to be the total valency divided by 2. Okay, now the next one is a minimum spanning tree. So we've got to write down in terms of n the number of arcs in T. So if we've got a minimum spanning tree of this, we've got 1, 2, 3, 4, 5 different nodes, and a minimum spanning tree won't have any arcs. So each vertex or each node is going to be connected to 2 vertices, but because it doesn't make any loops, it won't be the case of just divided by 2. Now the easiest way to think about this one is to perhaps don't think about this one that we've got here. Think about a very, very basic diagram. So let's say we've got 3 vertices. Now we want a minimum spanning tree. So they're all connected. So if you have 2 nodes, then 1 arc will connect them. For each extra node that we add, so at the moment we've got 2 nodes and we've got 1 arc that connects them. And for each extra node, we're going to need an extra arc. It's going to be 2. So let's say we add in another node. Doesn't matter where the arc comes from, but for every extra node to connect it, we need an extra arc. So 4 nodes is going to be 3 arcs. So whatever the number of nodes is, the number of arcs is going to be 1 less than that. So if, what does n stand for? A connected graph has n nodes. So for the minimum spanning tree, the number of arcs is going to be 1 less than the number of nodes. So it's going to be the number of nodes, take away 1, and that's going to be the number of arcs. And now the part 3, hence write down an inequality in terms of m and n, comparing the number of arcs in T and the number of arcs in V. So what we've got here is we've got the number of arcs in a connected graph, and then we've got the minimum spanning tree. So that's going to be the minimum number of arcs that we can have. So therefore, the number of arcs in a graph will always be bigger than the minimum spanning tree, which is going to be n minus 1, unless, let's say we've just got 2 arcs here, so 2 nodes here, and let's say the completed graph looks like that. The completed graph will be the same as the minimum spanning tree. So therefore, in a case like this, the number of arcs in the completed graph will be the same as the minimum spanning tree. So we get m over 2 is greater than or equal to n minus 1, which I'm hoping if we have a look at the answers. So what they've done here is they've multiplied through by 2. So we've got m is greater than 2 bracket n minus 1, but it says or equivalent, so it's absolutely fine. Okay. So then if we move on to the next question, let's shift this up here. So question 6. So linear programming, one that most people absolutely abhor, which is a cool word for hate. Okay, so what we've got to do is if we've got linear programming with x and y, minimize c equals 2x plus 3y. So that is our objective function. And we've got to do that subject to these constraints here. So we've got to add lines and shading to this answer book. And so the first one I'm going to do is have a look at this x is less than 8. So what we do is we draw the line x equals 8, which you should know. So my lines might go a little bit wiggly because for some reason it does on this if I use a ruler. But notice that this one, it doesn't say that it's equal to as well. So it means that when we draw the line x equals 8, which hopefully you should know is just a straight line going down, it's got to be a dotted line. Very often they ask, why have you done a dotted line, or why is this on a dotted line? It's because it cannot equal 8. So that's that one done. We've now got to draw the other line. So x plus y equals 8. All we do when we sketch these lines is we find coordinates that add together, or that make it work. So if I'm going to draw the line x plus y equals 8, x equals 0, y equals 8, or x equals 8, y equals 0, or any combination of them. So x is 4, y is 4, and then we join them up. So 8, 8. In fact, I've forgotten to do the shading there. If I just draw this first of all, and notice I'm going to draw this one with a solid line because it says it can equal it. So going back to the previous one with the dotted line, it says x has got to be less than 8. So therefore, we don't want any numbers that are bigger than 8, so we're going to shade out this side of the diagram. Then we've got x plus y is going to be greater than 8. So if we just take 2 points either side, let's take this point here, 0, 0, and we take this point up here, which is 6, 12. 6 plus 12 is greater than 8. 0 plus 0 isn't greater than 8, so we don't want underneath the graph. So we shade out this side of our graph. Okay, next one. 4y is going to be greater than or equal to 8. So again, we're just going to draw the line. 4y equals x. So therefore, I'm going to use a point 0, 0, because if x is 0, y is 0. So 0, 0 is going to lie on my line. And if I do y equals, let's see, y equals 2, and then 4 lots of 2 is going to be 8, so x would equal 8. So 8, 2. So let's draw in that there. So I've got 8, 2, which is this one, and 0, 0. And then we join those up. It doesn't need to be in different colours. Again, I'm just doing it just to make it slightly easier, because I know it's not the easiest to see. And you want 4y's to be greater than x. So what I'm going to do is I'm going to choose 2 points either side. I've got 12, 0, and I've got 0, 12. Now 4 lots of my y value has got to be greater than my x value. So 4 lots of 0 isn't greater than 12, but here 4 lots of 12 is greater than 0. So 4 lots of my y has got to be greater than x. So therefore I don't want, or equal to it, I don't want this side here. Show you that side there. And then that's that one done. And finally we've got 3y equals 9 plus 2x. This is just a regular graph now. So we've got to find a couple of coordinates that make that work, and then we see which side of the line that we want. So let's say x equals 3, and 9 plus 2 lots of 3 is going to be 9 plus 6 is 15, so y is going to be 5. And then again, what I'm going to do is I'm going to choose another number so that can be divisible by 3. So if x equals 6, 2 lots of 6 is 12, plus 9 is going to be 21, divided by 3, y equals 7. So then I draw in the line, gracious me, I draw in the line that goes through points 3, 5. So 3, 5 is here, and 6, 7, 6, 7 is there. So again, let's draw in that line there. I mean, there's loads of different ways in which you could do that. But I want 9 plus 2x to be bigger than 3y. So let's choose 2 points, one either side of the line. So let's choose 0, 10, and let's choose 12, 0 again. So 2 lots of my x number plus 9 is going to be greater than 3 lots of 0. So I do want this side. Let's just double check the other side though. So 0, 10. So 2 lots of my x number, so 2 lots of 0 plus 9 isn't bigger than 3 lots of my y number. That's going to be, so 9 isn't bigger than 30, so I don't want this side. So therefore I'm going to shade out this region here. Again, the more you do of these, the easier it will get for you. And that's it. And hence determine the feasible region and label it R. That's a nice quick mark. Use the objective line ruler method to find the exact coordinates of the optimal vertex V of the feasible region. You must, well, because what we want to do is we want to minimize this. Right, okay, so this is going to be quite tricky to try and represent on here. So what I'm going to do is I'm going to try and explain to you via the medium of pictures what it is I'm doing. So first of all, we've got to find out what this looks like. So what I do is I choose any cost, and I've got to find values that make that cost that value. So let's say I choose my cost to be, it's got to be a number that 2 and 3 go into. So let's say I want to make it £24. Let's try and find two sets of x and y values that make it £24. So I could have my x value as 12 and then my y value equaling 0, or I could have my x value is 0 and my y value as 8. And so if I do that, let's try and get rid of this stuff here just so we can see this. Right, so in fact, we know where our feasible region is here, so let's tidy up this diagram a little bit. So our region's got to be in there. That makes it a little bit easier. So now I've got to do my objective function line. So let's choose a different color. So 12, 0 and 0, 8. Now again, I'm just going to sort of reiterate this. I just chose £24 because I know that 2 and 3 go into it. I could have chosen £6 or I could have chosen £18. It's just arbitrary that I chose £24. And then what I do is I'm going to do this as a dotted line, but you could do it as a, well, in fact no, I'll just do it as a solid line. And that's our objective line. Now, if you imagine that my ruler, because at the moment my ruler is actually on top of that black line, and then if I push the ruler up this way, I'm finding a maximum point. So which will end up, if I keep pushing it up this way, I'm going to get to this point here. But what we want to do is we want to minimize cost. So what I'm going to do is keeping the gradient of the ruler the same, I'm going to go the opposite direction. So I'm actually going to push my ruler in this direction here until I get to the very end point of my feasible region. So if I push it on a little bit, then my ruler looks like that. If I go in a little bit further, my ruler looks like that. And then as you can see, as you go further and further, you actually get to this point here. And so this is my objective line here, which I've drawn clearly. And we've now got to find the coordinates of where these 2 points, so where these 2 lines have met. So calculate the corresponding value of C at V. So what we need to do, before we do that for part C, is we need to work out what that coordinate is. Now that coordinate was where my line 4y equals x and my line x plus y equals 8 met. So what I do is I substitute in, well, I solve this simultaneously. So my value of x is the same as 4y, so I can say that if I substitute x as 4y, 4y plus y equals 8. So 5y equals 8. So y equals 8 over 5. And bear in mind it says the exact coordinate, so keep it as a fraction. And then my x coordinate, if I look here, is 4 lots of my y coordinate. So that's going to be 4 lots of 8 over 5, which is 32 over 5. So 8 over 5, 32 over 5, they're going to be my coordinates. So again, I'll then go back and say 32 over 5, 8 over 5. Then it says calculate the corresponding value of c at v. So what I then do, once I've got my coordinates, I'm going to then substitute that into my objective function to find out what the cost is. And so I do 2 lots of 32 over 5 plus 3 lots of 8 over 5. And if you then do that on the calculator, 3 times 8 over 5, we get 17 and 3/5. So that is going to be our minimum cost, 17 and 3/5, which if it's in terms of pounds, 3/5 of a pound is 60 pence. So it's going to be £17 60 pence. What we've now got to do is we've got to maximise 2x plus 3y where x and y are integers. And we've got to write down the optimal values of x and y corresponding to this. Now this is different. I want to highlight this because it says integers. So what that means is we can't have 32 over 5 and we can't have 8 over 5. So what we're going to do is if we go back to our diagram here, we've got our objective line, and now we're going to push it to the other side. So what we highlighted up here, that's where we're going to try and push it to. However, now we can't actually be this point because we know that because this was a dotted line, that x can't equal 8. So we've got to push our line up this way. So if we push up a little bit further, we're going to get to this point here. If we push up a little bit further, we're going to get to this point here. But we've got to stop when we get to our last integer. So what we can do, especially if we've got a sharp pencil, we can fill in the integers here. So we've got 6, 6 there. We've got 7, 6. Now we can't have 8, 6, but we've got 8, 7. 8, 8 doesn't lie within it there. We've got 6, 7 there. So we keep going in that way, and if we use the ruler method, the last one that we get to should be this one here. So that's where x is 7 and y is 7. So x equals 7, y equals 7. So there are optimal values of x and y and the corresponding maximum value of 2x plus 3y. So 2 lots of 7 plus 3 lots of 7 is going to be 5 lots of 7, which is going to be £35. I'm presuming it's pounds. Okay, next, a further constraint, y is less than or equal to kx, where k is a positive constant, is added to the linear programming problem. Determine the least value of k for which this additional constraint does not affect the feasible region. So, let's have a quick look at this. So what does the line y equals something x look like? It would have helped if I hadn't have got rid of all of my lines. But I might need to use the mark scheme to help you out with this one. If we try and explain it first, when you draw the line y equals kx, so for instance, y equals 2x, x equals 1, so x equals 0, y equals 0 along the line, x equals 1, and y equals 2. So 1, 2 would line the line. So y equals 2x, looks like this. Y equals x over 6 means that x equals 0, y equals 0, and y equals 1, x equals 6 would lie on that line, so 6, 1 would lie on the line. So that looks like that. And what we've got to do is we've got to try and find out where, if we then draw the lines up, 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 or down, 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 the closest that it gets that it doesn't affect our feasible region. It says y has got to be less than kx. So let's see which side of the region that we shade. Let's go with this y equals 2x. Y equals 2x was where it goes 1, 2, 2, 4. So if we're looking at y has got to be less than or equal to 2x, we take points on either side. X is, so that's going to be 12, 0. That's going to be 0, 12. If we've got y equals less than 2x, we want this side here because 2 lots of 12 is greater than 0. So we want this side, so we don't want this side. So what we're going to do is we're going to try and keep going down from the top side until we get to our feasible region. And then when we get to a point which is just on the outside of our feasible region, that's what we're going to try and work out. So hopefully they'll have, here we go. So if we also have a look here, we've got our correct answers from the previous ones. So we are going to draw in our lines here, just like we've just said. So it's going to be up like that, up like that. But the one that doesn't affect our feasible region, because we know it goes through 0, is going to be this line here. So then we have got to work out what that line is. So that point there is 3, 5. So we should, because we've done C1 and C2, now we should be able to work out the equation of a line. The gradient there is 5 over 3, and it goes through at 0, so y minus y1, let's try again, y minus y1 equals mx minus x1. So y, and it goes to a point 0, 0, so y minus 0 equals m, and our gradient is 5 over 3, x minus 0, so that's going to be that. So we end up with y equals 5 over 3x, which, if we go back to the question, we're trying to find the value of k. So it's going to be k equals 5 over 3, which if you rewind the tape by 30 seconds, you'll see. Okay, next question. I believe this is the last one. And it's a huge one. Okay, so we've seen that we've taken 1 minute 24 at the moment. And don't worry, you will start to get quicker at this, and it's because I've been trying to explain everything in a bit more detail that it's taken this long. But worst thing happens, and you've got the answers up to 100% up to this point anyway, then we're doing okay. So, question 7. We've got a precedence table here, and they've drawn out the graph, which sometimes they get you to do, which we'll have a look at in another video. So what we've got to do is we've got to add activities E, F and I and exactly one dummy to diagram 1 in the answer book. So E has got to be preceded by A, and L's got to be preceded by it. So what we do is we draw in our line from so it's got to be preceded by A, so it's got to go from A to L. So that's E, and that takes 7 days. The next one is F. So it's preceded by B and C. Right, okay, so, in fact, if we just pause for a second, so, F has got to be preceded by B and C, as has G, but H has only got to be preceded by C. So what we're going to do is we're going to add in a dummy arc here. Because what happens is that E and F only share some of the, or sorry, H only shares some of the predecessors of E and F, so therefore we need a dummy arc. And it needs to be going in this direction here, it needs to be going this way, because others aren't dependent on C. So others aren't dependent on B, only on C. So once B and C are done, then F can start. So, and then what's dependent on F? L is dependent on F. So there you go. Oh, an arrow there. So that's F, and that's going to be 10. Because now 10, sorry, F is preceded by B and C, and L needs F to have happened first of all. And then we've got I. Now I is preceded by G and H, which is starting off down here, and what else needs to be done by I, and then L needs to be done by I. So that's going to be there, and I takes 8. Okay, so now we can just double check that L, E, F, and I, and J down here, the dummy from J, is going into it. What else has been affected? F, B, and C. Yep, that's handy for F, and then C. So H down here, that's only needs to be preceded by C, so B doesn't need to have finished. So that's why the arrow is going this way. Okay, so the next thing we have to do is fill in the early event times and the late event times. So what we start off by doing is a forward pass. So the forward pass always starts with a 0 here. And then the earliest time that A can be finished is 5. The earliest time B can be, the earliest time C can be finished is 8. Now, a lot of people make the mistake of saying the earliest time that B can be finished is 7. However, 7 is also dependent on C finishing. So C, it's going to be 8 minutes until C is finished. So therefore B can't be finished until everything going into B is finished. So therefore that's going to be 8 as well. Okay, D, the only thing that D is dependent on is A. So D can finish at 10. And then if we have a look at this one down here, G is dependent on B finishing and H finishing. So 8 plus the 4 is going to be 12, but 8 plus this 9 is going to be 17. So it's going to be 17 before they can all finish. Then if we have a look at this one here, we've got to finish J as well. So 17 plus J, so that's going to be 29. And then for this one here, everything's got to finish. So E's got to finish, F's got to finish, I's got to finish, and J's got to finish. So 5 plus 7 is going to be 12. 8 plus the 10 is going to be 18. 17 plus 8 is 25. But you've also got this 29, which has got to be finished here. So that's going to be 29. So then we have a look at this one here. So you've got 10 plus the K, so that's going to be 17. But L's got 29 before L can start, so another 10 minutes or 10 hours, whatever this thing is. On top of that is going to be 39. So then what you do is you do a backwards pass. So you start off with 39. And what's the latest time then that K can start so that it's finished by 39? If it's only going to take 7 minutes, then it can start at 32 minutes and it still be finished in time for 39 without delaying the project at all. When's the latest that this one can start and still be finished? Well, the latest it can start is 29. It's going to take 10 minutes and then it's going to be 39 minutes. So when's the latest this one can start and still be done by 29? Or if it's 29 and it's not going to take any time, it's going to have to be 29. Okay, when's the latest that this one can start and still be finished for either 32 here or 29 down here? So if we take 7 away, this one can start at 22, and if it starts at 22, it's going to take 7 minutes and still be done for 29. 22 plus 5, that still gets done in time for 32, so 22 is the latest that this can start and still not delay anything. So let's work back to this one down here. Let's get rid of some of the arrows so you can see what I'm pointing at. So we're looking at this one down here now. So that's got to be, that's got to be done for 29. So in theory, that could be 21 then, still be done for 29. However, if this one starts at 21, 12 minutes later, it won't be finished in time for 29. So that one's got to be 17, so that it's finished in time for the 29 over there. Then we have a look at this one here. So that's got to be 8. So this one is reliant on it. So that could start at 19 and still be finished for that one. This one can't start at 19 and still be done for 17. But it can be finished for 13. So if that's finished for 13, so if that starts at 13, then this one's going to be finished for 17, and this one's going to be finished for 29. So this one here, this one needs to be finished for 13, so if we put 13 there, that's fine for this one. But for this one, if we start at 13 and then we go for 9 minutes, that's not going to be done in time for 17 minutes. So that one can't be 13. So if we take 9 away, that's got to be done for 8. And then we go back to the beginning, and that one's got to be 0. So there we go, the completed diagram for early and late times. So if we just check that, 5:22, 8:13, 8:8, 17:17, 29:29, 29:29, 10:32, and of course the 39:39. Right, calculate a lower bound for the number of workers needs to complete the project. So what we do for this one, for part C here, we've got to add up all of the event times, and we divide it by the finishing time. So if we add up, so this is part C, 5 plus 7 plus 8 plus 5 plus the 7 that we've put down here, don't forget that one, plus 10 plus 4 plus 9 plus 8 plus 7 plus 10 plus 12. Add those together, we get 92. So then we do 92 divided by the project time, which was 39. We get 2.35. So we get, for C, 2.35. So therefore we need to have 2.35 workers. Obviously you can't have 2.35 workers, but you don't round to the nearest number. If you're going to need 0.35 a worker, it means that you're going to need to have an extra worker. Even if it was 2.001, you'd still need that extra worker to make it up to do the extra 0.001 person's work. So you're always going to round this up, so that's going to be 3 people. So we end up with 3 people there. Schedule the activities using the minimum number of workers so that the project is completed in the minimum time. So okay, we need to have another copy of that there. So if I just get another one of these, and as if by magic it appears, what we're then going to do is we're going to have our 3 minimum workers. So we're going to have worker 1, which is going to go here, worker 2, which is going to go here, worker 3, which is going to go here. Now when we do this, the first thing we do is we're going to do the critical path. So worker 1 is going to do the critical path. So that's this one here. Now the critical path is the path where it's got no float whatsoever. So for instance, this one can start at 0, end at 8, and it's going to take 8 minutes. There's no float there. It's not necessarily the ones in between two things where the numbers are the same. So for instance, C and H are 2 critical values, but I isn't a critical value because it goes between 17:17 and 29:29, so that's a gap of 12 days or 12 minutes, but this one only takes 8, so that's actually got a float of 4. So the critical activity though is J. We have that one there, and then we go across to this one. So the critical activities we're going to give to worker 1, and that's going to give us some marks. So the first one is going to be 0 to 8, and that's activity C. And then we've got activity H, that's another 9 minutes, that takes up to 17. And then we've got activity J, which takes up to 29. And then we've got that dummy activity, which we don't include, and then we've got 29 up to 39, which is this one here. Okay, so now we've got to do we've got to do the worker 2. And the way we start off this second worker here is that we've got to have a look at, okay, so we've done C, we've done H, we've done J, we've done L. So we now have a look at the next most critical that can start at the time 0. So we start the clock at 0, and the most critical one is the one with the earliest late event time. So we're looking at the bottom numbers now. So we've got 13 here, and we've got 22 here of the ones that can make us start. So the most critical is 13, because that's the earliest finishing time, or earliest late finishing time. So we're going to start off this guy for 7 minutes, and he's doing activity B, and so that's that one done. And then we're also doing, so worker 3 can do A, because we're using the minimum number of workers. So we're using 3 workers, which is what we worked out in part C. Then A goes on for 5 minutes. Okay, and then once we've set those, we then wind the clock forward. So we now go forward, so 0 minutes, everyone's busy. 1 minute, everyone's busy. 2 minutes, 3 minutes, 4 minutes, 5 minutes. As soon as you get to 5 minutes here, worker 3 becomes free. So now, the ones that can start after 5 minutes are this one here and this one here. And so what we do is we have a look and see which is the most critical one. So the most critical one is the one with the earliest finishing late event time. So that's going to be this one here. So worker 3 starts on E, and that's going to go for 7 minutes. So it starts at 5, so he's going to go to 12 minutes. Okay, so then that's 5 minutes, and we've given worker 3 another job. So we fast forward the time, 6, 7 minutes, and now on 7 minutes, worker 2 becomes free. So on 7 minutes, so we've just done this one here. So we can't start F or G yet because they can only start after 8 minutes. So the only one that's available to do is D. So what we're going to do is we're going to give activity D to worker 2. So he's going to start that on 7 minutes, and it's going to take 5 minutes. That takes us up to 12. Okay, so now the clock's on 12 minutes. And so the ones that we can do after 12 minutes, we've still got F to do, we've still got G to do, we've still got I to do, and we've still got K to do. So they're the only ones that we haven't coloured in yet. So worker 2 is the one who takes the highest priority case. He's the one that's further up. So we have a look at the ones that he can do. So the time is 12 minutes. So the only ones available to him are F and G. And from F and G has got to be finished by 17 minutes, so we're going to give that one to him. So 12 minutes plus 4 minutes is going to be 16 minutes. So he goes there, and that's G done. But worker 3 is also available on 12 minutes. He can start activity F. So that's going to be another 10 minutes. That takes him up to 22. That's F. And now we've got 2 activities. Also, we could have given activity K, because that could start at 10, but that's got a really late finishing time, so we don't include that one. So the only activities that we haven't done now are I and K. And again, you can just sort of keep check by doing A, B, C, D, E, F, G, H. I is one of the ones, and J, K is another one, then L, and that's all of them. So it's just I and K that we need to do, and I is the one with the earliest late event time. So the most pressing one, that can start at 17, so as soon as 2 finishes after 16 minutes, but we can't start I until 17 minutes. So we move the clock forward until 17 minutes, and then he can start. So it's going to go from 17, then for another 8 minutes, so that's up to 25. None of this is that tricky, but it just takes time, and you need to have done it a few times. Once you start to see how it's done, it really is quite simple. It's just a matter of going through it really, really slowly. Don't worry that the time's gone over 1 hour 30. All we're doing is we're just concentrating on the method for this one. And then once we've done I, we've only got one left, which is K. So we were on 17 minutes, which is when worker 2 started. Then we fast forward the clock until the next person's free. So fast forward the clock until 22 minutes, which is when worker 3 finishes F. Then he can start K, or she can start K. Sorry, I don't mean to be sexist. So worker 3 can then start K. So it's after 10 minutes, which is when the earliest it can start. It goes on for 7 minutes. So starting at 22, going off 7 minutes, takes up to 29. I would hate to mark this. Apologies if there are any teachers watching this that do mark it. And that's it. And that's all of them done within the allotted time. So that's our minimum workers, 1, 2, and 3. And it's all done without lengthening the project, which still remains at 39 minutes. I believe that's it. Just check. In fact, we can check the answers. So, yeah. I think that's okay. Okay, thank you very much, boys and girls. Any questions, of course, leave them in the comments box.